My name is Danny Borsboom. I am a professor of psychological methods here at the University of Amsterdam. And I teach this class as a guest class for Roeland and for this course to, well, sort of tickle your brain about the question what measurement and statistics have to do with each other. And this is a bit of a tricky question, but I want to hang it up on a very concrete point, a very concrete question that often arises in statistical analyses and that you've also encountered before. Namely, you often see that tests require that variables are measured at the interval level, right? And if that's not true, and you analyze the data with a t-test or an ANOVA or something that assumes the interval level of measurement, then the sky falls on your head. And the methodology police comes to pick you up and lock you up. Right? SPSS even has a warning sign if you try to do a t-test on dichotomous variables, so 0, 1 variables. It says, oh no, that's the wrong level of measurement. So, why is that? Where does that come from? Where does this type of question or norm, what is the basis for this kind of norm? And how strict is it? What really happens when I actually push the button and I do the t-test on the dichotomous variable? You know, will the computer explode? Why is this so tricky? And so that question goes to the heart of the relation between measurement and statistics, which is a really interesting relation. And it's also important for psychologists to understand something about this relation. Because measurement in psychology, in contrast to measurement in physics and biology, is difficult. It's extremely difficult and it's wrought with problems and it requires a very nuanced thinking about the role of measurement in statistical analyses, but also in real life. So that's one of the goals of this class, is to take this kind of relation, which is one of many relations you could take, to show you that there is something beyond the cookbook, right? So that beyond the field and SPSS sort of lines, there are deeper considerations, but also that these considerations are human considerations and that these rules do not come from heaven. There is no methodological Bible. In fact, it's a ground point of science that there is no methodological Bible. These things depend on people thinking and they shift. So that's also good, very, very good to understand and to keep in mind that these things are not fixed. They are not written in stone. Now, when we go beyond the cookbook, it's a bit tricky because if you lift the tapestry, then under that tapestry there is a depth of stuff. Okay, so methodological questions, once you go beyond the it's like when you have children and they ask why questions, so you can say, well, why do you do an ANOVA? Yeah, well, because I'm interested in experimental design, so yeah, but why do you do an ANOVA? Because the variables are normal. Yes, but what does that mean? Abyss. Okay, so it can be a bit scary. But stay calm, relax. This is an overview of what I want to say. I want to say a little bit about the history of measurement in psychology and the history of the word measurement, because the tension between statistics and measurement theory actually has a lot to do with that. Then I will demonstrate what these scale levels really mean, nominal, interval, ordinal, ratio scales, and how they depend on transformations that you can do with the numbers you assign to objects or people in our case. And then I will show you with this beautiful instrument here how that works in cases we really understand well, which is not psychology. And then I will say a little bit about implications for statistical practice and how this has given rise to the measurement statistics debate, as they call it. Right, so that's it. First, let's revisit a little bit about the history of measurement. Of course, we know that there is such a, you don't know that, but I know that. There is such a thing as measurement theory. There are big books about it. There's psychometrics, there's mathematics, there's set theory and all kinds of things. But of course, measurement is much older than any philosophical or conceptual or mathematical or logical or methodological or statistical analysis of measurement, because the Egyptians, for instance, had measuring rods. They could build pyramids, so they obviously understood a lot about measurement, and they didn't have any set theory or whatever. So measurement, in a very non-trivial sense, is really, really old and really, really basic, and I personally think grounded in our biological system. We are equipped with assessing certain relations quantitatively, and what humankind has done is, expand these to cover ever more things that you could actually express in numbers, express relations between things in numbers. And as science progressed and the scientific revolution arose and people started applying scientific thought everywhere, it was only a matter of time that somebody started thinking, why couldn't I actually measure psychological attributes? Could I measure intelligence, aptitude, personality? And the first person who had these thoughts is this guy here, Francis Galton, a nephew of Darwin, by the way, and a polymath, as they call it, somebody who did a lot of different things. So he invented the first intelligence measurements in this laboratory here, but he also was the first person he invented the correlation coefficient. Think about that, that's amazing. He invented meteorological maps. That he did on the Sunday, I guess. And he also invented the fingerprint method. Yeah, you had that in these days. So he also invented intelligence measurements, and the idea that you could actually measure aptitude or skills or the hereditary intelligence, as he thought of it, by giving people different tasks. And when he looked at relations between these tasks, he was very interested in the relations between the skills or the length or the bodily composition or whatever of children and their parents, because he was interested in heredity. And that's also why he invented the correlation coefficient or the regression idea. And this is one of the first graphs of that. The length of sons and the length of their fathers in a scatter plot, the first scatter plot. So people started this idea. They started giving different kinds of tests to individuals, making number tests or verbal tests or reaction time tests or all these kinds of tests. And then they started applying the correlation to them, because the correlation was new. The correlation was like, the fMRI machine of 1900. Just invented, so everybody applied correlations to everything, and so they applied it to all these intelligence measures. And then a student of Galton, this guy Spearman, found something really weird in the composition of these correlations. Here you see a very big table, which you cannot read, but it's a correlation table that gives the correlation between all different kinds of intelligence-related tests, cognitive tests. Tests that your grandmother would say, well, looks like a puzzle, right? It doesn't matter what kind of puzzle, figural puzzle, number puzzle, verbal puzzle. And what's bizarre about these correlations, and one of the great findings of psychology actually, is that all of these things are positive. And that's called the positive manifold. So whenever you correlate in the population something that your grandmother would say, well, that's a puzzle, and something else that your grandmother would say, well, that's a puzzle, they will correlate positively. People who are better at one thing generally are also better at the other thing, on average, right? It's a correlation. It's not the deterministic relation. Wow. So this gave rise to the idea that maybe if you... Why is this? Why is this? Well, thought Spearman, there obviously must be some sort of central general intelligence faculty, you know, some property, mental energy force that people differ in, and that's what creates all these correlations. So just like you could have, for instance, you could have these different items, so these are different kinds of puzzles, and they all correlate positively, and the idea is, well, that must be because there's a general intelligence factor that's behind these things and that causes these correlations, right? So the correlations are essentially spurious. They arise because of the dependence on general intelligence. And if that's true, then you can actually add the responses to all these kinds of test items. You can compose a total score, just count how many puzzles did the person solve, and take that as an indication of the underlying general intelligence factor. And people who score higher are more intelligent, people who score lower are less intelligent. Actually looks pretty much just like what the Egyptians did with their measuring rods, just measurement. So psychologists became very optimistic. They thought, we can measure just like the physicists do, and we will have our quantitative science just like the physicists. So psychologists get very comfortable in using the word measurement in their research. And total scores on IQ tests are interpreted as I miss a word there, as a measure of general intelligence. And some of the more audacious psychologists start saying, well, there's actually no essential difference between physics and psychology. And especially a guy in psychophysics, very famous psychophysicist, somebody who studies the relation between physical quantities like light intensity and subjective quantities like how bright you think the source is. S.S. Stevens, he also uses the logic of measurement to set up all kinds of skills, and he goes really far in the quantitative interpretation of these skills. And especially important was the so-called just notable difference, which is the smallest difference you can note, and you can sort of add them. You can say this sound and this sound, well, they are composed of so many just notable differences, so we can measure the distance between these sounds in their subjective loudness.